10th session, that is the last session for the speech. This is the 6th day for session. So, firstly, I would like to request our coordinator, Dr. to felicitate Dr. Amit Kumar with the implementation. Now I would like to introduce Dr. Amit Kumar before you. His professional qualifications. In 2008, he completed his Bachelor of Technology in Mechanical Engineering from Honolulu Institute of Technology. Then in 2010, Masters of Technology Engineering Mechanics, Indian Institute of Technology in Delhi. Then in 2020, he completed his PhD in Applied Mechanics from the Indian Institute of Technology in Delhi. Regarding his professional experience, he has vast professional experience. In 2010, he joined the CSIR CMUI and is still there, working as the principal scientist in the Advanced Design and Analysis Group. Other than this, he has other working experience as guest scientist in Germany from October 2014. And he is also working as an associate professor, honorary associate professor, Faculty of Engineering Sciences, ACSIR, University of Oldenburg, Germany. He has many such working experiences as guest scientist in Germany, starting from 2014. His areas of scientific interest are computational solid mechanics, wave propagation, multifunctional structures, wearable exoskeletons. Regarding his achievements, this is also very vast as his professional experience. So, in 2014, he started working as guest scientist in Germany. In 2019, he was a visiting faculty at the Metal and Industrial Development Institute, Addis Ababa, Ethiopia. In 2021, he got the Best Presentation Award at the 7th Asian Conference on Mechanics of Functional Materials and Structures, Tohoku University in Japan. In 2022, session chair of the session Numerical Simulation in the 13th International Symposium on Plasticity and Impact Mechanics, NUPLAS 2022 at IIT Madras, Chennai. In 2023, he is a recipient of CSIR Young Scientist Award, Engineering Sciences for the year 2022. Lastly, the latest one, the visiting scientist at the University of Oldenburg, Germany. And he is a professional body member of the Institution of Engineers India. And he is a member from 2019 till date. So, with this, I welcome Dr. Amit Kumar for his speech.
Thank you, sir. It is my pleasure to be here at
training for yesterday and new on and rocket, which is not actually from one project. There are two projects which we have worked on, and I am representing some of the things of the developments that we have done in the field of hand etc. Is the sound okay?
So can I speak like that? So maybe those at the back can come at the front then. No, I can directly. I think I will start now. Yes. So, I am principal scientist at Advanced Design and Analysis Group at Central CSIR Central Mechanical Engineering Research Institute. So, I think most of us have seen exoskeletons by now. A lot of movies have started to show exoskeletons, and the developments have been ongoing from almost 10 to 15 years. In the world, large number of developments have been happening. But mostly the exoskeletons are still either in lab, prototype phase, or at max some commercial products which have not got that much acceptability. But what is expected is that because one reason is that they are right now very costly. So with time, it is expected that their commercial uses will be more and more present in our daily life. Now that will depend on application to application. Some applications will adopt exoskeletons fast. Some may take some time. Now I think you must have had some speakers who spoke about lower limb exoskeletons. So what I will be presenting is about the exoskeletons for human hand. And what are different applications? So most prominent that one can think of is rehabilitation. You know, when a patient suffers from stroke or any other hand function impairment diseases, then their hand function is lost, and in that case they need some assistance in their hand function, hand motion. So there the exoskeletons come into picture. Then in remote handling. So what is remote handling is, I am sitting here, there is a robot in, let us say, the other building, and I want to operate there. Why? Because that may be some radioactive environment or biohazardous environment, and human cannot go personally there. Then I need to operate that robot from here itself, and to do that task is the remote handling. Now in remote handling, there comes the concept of haptics. Because in most conventional cases of remote handling, the person who is operating here is getting the visual feedback from the remote side, but he is not getting any sense of touch or interaction with the objects or with the environment on the remote side. So, haptics come into picture. Now, haptics also involves a different kind of feedback. So, haptic feedback has two major kinds. One would be the feedback to the force feedback or the kinesthetic feedback. What is kinesthetic feedback? Is that, so let me talk about the other type of feedback. That is about the sense of the friction, sense of temperature, sense of pressure. So in kinesthetic feedback means if my leaf is what is kinesthesia? If my finger is straight, I don't need to look at it because I know in the space where it is. This feedback or that sense of knowledge of your finger is the kinesthesia. So when you provide the force on the finger such that, let us say in the remote environment I am grasping some object, as soon as I hold the object, I get a feedback that my fingers have touched the object. So I should get that kinesthesia by stopping my fingers in this space, although there is no object in the master side. Okay, so we will go into the details of all this in the next discussion. Let me start with what is exoskeleton. Exoskeleton is a mechanism placed on or around the hand with some interaction points fixed with finger digits and palm. So some mechanism that may be placed either directly onto the fingers or around the fingers. It has some interaction points, that means it attaches to your fingers and palm at different locations. What are the functions of the hand exoskeleton? One of the major functions is the measurement of motion. We want to measure in real time what the movements of the hand. That is the first function. Then the force transmission. Force transmission is, as I discussed, if you want in certain cases to also apply the forces onto your finger, then exoskeleton is the best way to achieve that. So it allows the force to be transmitted in safe and controlled manner. That is the force distribution. What if you don't want, for example, your finger has 3 joints. You want to apply the force on your finger, but what you don't want is to use 3 actuators. Using only one actuator, you want to apply the forces on all the 3 joints. That is the force distribution. You want to distribute the force from a single actuator to different joints of your finger. So here many people actually confuse the distinction between an exoskeleton and a robotic hand. What is robotic hand? Robotic hand is something which replaces the hand. Okay. Here to be using, as I told you, if you want to do remote handling, there we will need a robotic hand to perform the task. For the amputees, so if due to some accident you don't have your biological hand, then you are given some robotic hand as an attachment. How is it different from exoskeleton? Exoskeletons require your original biological hand. Even in rehabilitation application, you need your hand to wear the exoskeleton. Okay, for example, this exoskeleton, it cannot operate without a hand. Its motions will be completely different. It will not achieve the functions that is needed. So what is the exoskeleton? Is some mechanism which is placed on your hand. There are certain requirements it should be complying with the anatomy of the hand. It should be safe to wear. It should not apply sudden and very high forces onto your hand. It should be comfortable to wear. So these are some general design requirements, irrespective of what you are designing the exoskeleton. Effective force reflection. That means it should not happen that your exoskeleton is producing very high force, but still some force. Only a part of the force is being reflected onto the finger. This is one of the important requirements, that the center of rotation of the mechanism should coincide with the finger joint. Now, if your mechanism is trying to rotate around the center which does not align with the center of your joint, skeletal joint, then what will happen? Then the reactions will appearing on your joint. Okay. So it is likely to damage your joint. Hand size variability. What is hand size variability? Is let us say I design some access curtain for my hand, and obviously if some other person wears it, his fingers length may be slightly different, the diameter will be slightly different, so it should accommodate the hand size. And obviously it should be lightweight. If it is heavy, then it fails the purpose. User cannot wear it for a long time. Now there are requirements which are application specific. What do I mean by application specific? As I discussed some of the applications, one is the rehabilitation. One of the requirements of rehabilitation is that let us say I have an access curtain and I am doing rehabilitation after wearing that. I may need to interact with some objects, real life objects. So the mechanism then cannot obstruct my one thing is natural motion, as well as it should not obstruct my working area of the palm, which I use for traveling. There should be no obstruction on the palm. Obviously, the hand is already weak for the patient, rehabilitation exercise. So the exercise should be easily available. We also need motion tracking for rehabilitation to track its recovery parameters like active range of motion or anything, any other parameters. Then the assistive exoskeleton. What is assistive exoskeleton? I have not talked about it yet. It is slightly different from rehabilitation exoskeleton. What is rehabilitation? I told that I need to use I need some assistance in moving my fingers. So sometimes passive motion is provided. That is called the continuous passive motion. You might have seen if somebody suffers from stroke, then for a few days of his recovery, you will see that the doctor will come to the patient and he will just hold his fingers, and what he will do is some exercise like that is to reduce the stiffness in the muscle. This is called the continuous passive motion. Also, now what is assistive exoskeleton? So assistance is needed for both rehabilitation, but what is assistive exoskeleton is that let us say in my daily life, that is not just while doing therapy or exercises, but in my daily life, if I want to pick this up and drink the water, I want to hold different objects. So at that time I need assistance. Now, what is the special requirement in this case? One of the things is the portability. For rehabilitation exercises, I can do on a particular table, let's say half an hour session per day, 1 hour session per day, that's it. But assistive exoskeleton has to be with me 24/7, or at least while I am awake. I need to do some task, I need to go to the kitchen, take a sip of water. Then I need some exoskeleton which I can wear while walking. So its power source should be such that it gives me some backup, and it should be lightweight, etc. This is assistive exoskeleton. What is written ADL is activities of daily living. This is applicable for the activities of daily living. Motion tracking is usually not required. Some crude device which can provide me some force as and when I need it. Not a lot of recovery parameter measurements are needed in this interaction with real objects is required and there should be no obstruction on my palm side. Now I talked about remote handling and haptics. So one of the extension of the remote handling is the VR exoskeleton. What is VR application? So I talked about manipulating objects in the remote environment. Now a lot of times we need to do some tasks or manipulate objects in the virtual environment. What is virtual environment? That is, you have some end effector and objects in the CAD space, in the computer space, and you need to perform some tasks there. That is the VR exoskeleton. Now, what are the requirements? Design requirements for VR exoskeleton. That is the instant adjustability for different tasks. So, this exoskeleton ATL may be like especially for drafting, but in the VR exoskeleton, it sometimes even use the gesture system. So it should adjust for different type of tasks that I want to do with the remote environment. Let's say I want to do some pitch or farmer task. It requires an efficient finger tracking. Why? Because on the remote side, there is a robotic hand which need to exactly copy your own hand. So if your motion is not exactly captured, it is difficult, it will not be possible to do remote manipulation tasks. Independent finger control. For activities of daily living, you may use single actuator to actuate all the 4 fingers, right? Let's say I want to grasp a glove. But here for remote handling, where there are large type of tasks, and actually it is working in a master slave mode. All these don't work in master slave mode. These work in master slave mode. What is master slave? The user during the exoskeleton is the master. Slave is the either remote environment or the virtual environment, which will copy my finger motions with high rate. Now there are certain other selections or design decisions that we have to take for designing. What should be the hand mobility? What does hand mobility means? How many fingers do I want my exoskeleton to have? Like 3 finger exoskeleton, 2 finger exoskeleton. So these are different types of hand mobility, offer different types of hand mobility. Okay. Now, what is the finger mobility? Finger mobility is how many joints do I want to actuate in a finger? Whether just a single actuator, whether I want only one joint to be moving, do I want all the 3 joints, do I want independent actuation of the 3 joints? That is the finger mobility. Number of interaction points, actuator selection, which actuator to use, pneumatic, shape memory alloy, do I use DC motors, mechanism selection. So that is the how many linkages do I have in my mechanism transmission system. Do I want a rigid transmission? Do I want a geared transmission? Do I want a tandem-based transmission system? The dynamical structure of hand. So, what is the total degree of freedom of the hand? It is actually 21. So basically, our finger has 3 joints. Each of the joint has one flexion extension motion. This is called the flexion extension. This is some of the terminology of the joint. So I'll explain it much quicker than reading this right. So the farthest joint, it has 1 degree of freedom. It can only have flexion or extension. This is called the DIP, that is the distal interphalangeal joint. The middle joint is called the proximal interphalangeal joint. It also has single degree of freedom. The third joint can move flexion, extension, or adduction, abduction. This motion is adduction, abduction. So it has 2 degrees. So each finger has 4 degrees of freedom of thumb. And this joint is called MCP joint. MCP joint means metacarpo interphalangeal joint. Carpo, metacarpo. So this part is called the metacarpal. These three are phalanges. So metacarpo, interphalangeal. In the thumb there is only one IP joint, that is called interphalangeal, because there are only 2 phalanges. And this is MCP, same as metacarpal phalangeal. And the joint at the bottom, this is called the CMC joint, carpometacarpal. Now we will see some types of exoskeleton and exoskeleton. So we can categorize them based on different criteria. Based on application, obviously we discussed hand rehabilitation. This is one of the assistive exoskeleton. This example, this exoskeleton is developed for VR application. One advantage for VR application we have is we don't need to keep our palm free, right? If you remember my requirement presentation, these should have no obstruction on palm side, but there is no such requirement for remote handling exoskeleton and the VR exoskeleton. That is what we see here. These are the different rods coming. Obviously, while wearing this exoskeleton, I cannot do any task, but I can do the task on the remote or the VR environment. Now, based on the mechanical structure, there are exoskeletons which are based on the rigid linkages mechanism. Okay, for example, this one. So I have not mentioned the reference for this because this is developed in our lab. So this is only one for one finger. This is the mechanism. I will cover it in detail after some time. But what is the advantage of having the rigid linkage mechanism? Is that I can apply the bidirectional. What is bidirectional means? I can give the assistance for the flexion as well as for the extension. Okay. Now there are tendon-driven exoskeletons, in which a tendon is attached to the finger, which is then pulled by some actuator. Now one issue with this is that it can only apply the forces in the extension direction, not in the flexion direction. Now the third category is that of compliant exoskeleton. The example of that is where the pneumatic actuators are directly placed on the finger, and then they can be supplied with the muscle there to provide the assistance. We can actually provide both flexion and assistance using these actuators. But only problem with these actuators is obviously I cannot do position control. So if I want particular position, direct my finger to a particular position, I cannot do that accurately because of the compliant structure, because the air is compressible. So control using these pneumatic actuators is difficult. And what is also difficult is the measurement of the force. How much force is being applied? There is no structure to measure the force. Here I can measure using different sensors. I can apply a force sensor and I can measure how much force my hand is applying, how much force is being generated. I cannot do the motion sensing also here. Now types of resistors are based on the degrees of freedom. Now what is the degrees of freedom? That is the number of independent joint motion allowed in the mechanism. So based on that we can divide the mechanisms into two categories. One is the redundant mechanism, another is fully constrained mechanism. What is the redundant mechanism? The degree of freedom of a single finger mechanism is greater than 1. In fully constrained, the degree of freedom is exactly 1. What I mean to say by that is, if I have some mechanism fully constrained means there is only one configuration of the finger possible when the input is single. So a single input, there is a single output. Output means the configuration of the finger. Okay. So if we have some mechanism like this, if I move this point little bit away, then all the joints will have to adjust to that change in the input position. But how are these mechanisms redundant? If you see here, it applies directly onto the finger, right? Now what can happen is that for the single input, endpoint is fixed, but within endpoint I can have different angles of my finger. Okay. In the redundant mechanism, for example, in this mechanism, my fingertip position is fixed relative to my hand, but it does not constrain all my joints. If the final position is like this, I can also have this position to this angle or some other angle. Right? So there are 3 joints. I can adjust the joint angle such that the final fingertip position remains same. This is the redundant mechanism. Why is it better to have redundancy in the mechanism? When you have a redundant mechanism, it allows minor movement. So it makes it easy to quickly adjust little bit the task. Right? You are doing like this, you can go like this, right? Very fast. Another thing is that it cannot impose the strict finger synergies. So finger synergies is a complicated term. Finger synergies means okay, one simple example is like this. So if I want to move like this, even though I am only trying to move my PIP joint, but you will see that DIP joint moves automatically. Such motions, there are many such motions in human body where one tries to move one particular joint but the other one moves automatically without any control. Those things are called synergies. Now when we can design one, it is let's say 1 to 1 to obey that synergy. But when we have something like this, then if I apply on the fingertip force, then it may make my finger to go out of this synergy. But if this was some exoskeleton where it is 1 to 1, that is degree of freedom is 1, that means if my input point is not moving, I cannot make any change in the relative joint angle. Now, okay. What is the one disadvantage here? One disadvantage can be considered as, let us say I have some synergies which are different from other things, or some condition. Let us say my this joint is stiff, and if I apply excessive force, it pains or it gives me discomfort. So in that case, this mechanism will help distribute that motion to the other one, because it is degree of freedom is more than 1, right? But in this case, you cannot transfer motion from one joint to the other without giving any particular effect.
Take for 5 minutes.
Placement of mechanism. Exoskeletons can be categorized as the palmar exoskeleton. It is placed inside the palm like this. Although the drawback is that it cannot be used for assistive application or any application which requires our grasp to be closed fully. Maybe to some extent it can be used, but not for the full grasp. Lateral placement. Lateral placement means the mechanism is placed either on this side or on that side. The problem here is that I cannot give assistance to my middle finger, right? Only the side fingers can be given. Third is the dorsal. Now this is the, I think 95% of the exoskeletons come in this category, where the exoskeleton is placed on the dorsal side. This side, back side of the palm is called the dorsal side. On this side, if we place the mechanism to apply force on the finger, then it is the dorsal mechanism. These are some of the exoskeletons for rehabilitation, which are actually lab prototypes. So they just driven by cable. You can see the cable is coming to the fingertip, and it is actuated by, I don't know, there should be one more slide. Okay, sorry. So there are 2 more slides on the types of exoskeleton. One is, so it is based on the degree of actuation. That means how many actuators are provided in the exoskeleton. One is under actuated, fully actuated but coupled linkage, fully actuated but independent control. Let me come to that one by one. Under actuated means degree of actuation is less than degrees of freedom, which is usually greater than or equal to 2. So as I discussed about this exoskeleton, which we are actuating. Basically, when the degree of actuation is less than degree of freedom, then it is called the under actuation. Okay. Degree of freedom, I told you, is that how many independent motions are possible and how many are you actuating out of those. So if the degree of actuation is less than degree of freedom, then it is under actuated. Fully actuated means degree of actuation is same as degree of freedom. But I told you about this exoskeleton is that it has degree of freedom 1. Means for a single input player, there is only one configuration possible of the finger, and if the obviously there is 1 degree of freedom, we can only actuate that 1 degree of freedom. So degree of actuation can also be only 1. So motion of all joints is physically linked using 1 degree of freedom linkage. Now what is this fully actuated but independent control? Here the control is not independent. Means what does independent control mean? If I want to apply the force only on this joint, not on this joint, not on this joint, it is not possible with this exoskeleton. Okay? So it does not support the independent control. What does independent control mean? Here if you see these joints, they can be in this mechanism, they can be actuated separately by attaching actuator to these places independently. Then what will happen? That I can apply one actuator is connected to this place, one actuator is connected to this place, another actuator is connected to this place. So for each joint there is a separate actuator. The degree of actuation is 3 and degree of freedom is also 3 because the mechanism is such that their mechanism for this joint does not obstruct this one, but they are independently moved. So this is the fully actuated but independent control. Now based on mobility, as I told, hand mobility means number of assisted fingers, whether those assisted fingers are independent or coupled, that is also one aspect of the hand mobility. Finger mobility means number of actuated joints, how many joints are actuated, again whether they are coupled or independent, and number of points of interaction. If you see this exoskeleton, what are the number of interaction points? Here the exoskeleton is attached to the distal phalanx, middle phalanx and the proximal phalanx. There are 3 points of interaction. In this one, the exoskeleton is attached to the middle phalanx and the proximal phalanx. So there are 2 interaction points. This is single interaction point. Actually, here the exoskeleton is attached to only the first phalanx, proximal phalanx. But its degree of freedom is 1 because here the motion is provided only to MCP joint. When I actuate this, motion goes only to this joint, no motion goes into this joint. This also has one interaction point like this, where the actuator is attached directly to the fingertip. But here, the 3 degree of the mechanism degree of freedom is 3 because it actuates all the 3 joints. These are some exoskeletons which are commercially available. Actually, this I will not just only the sensing gloves which only do the motion sensing of this actuator. There is no actuator, so they don't provide any assistance. Now exoskeletons with assistance, you see this hand of rope from down. But look at how the here. So if you see, you will see these linear electromechanical actuators, where each figure, obviously what is popularly known about these actuators is that they are not back drivable. That means my hand is completely like constrained. I cannot try to move it. I don't get any freedom to move. Whatever the actuator position is, I have to constrain my hand to that. You see, this is the weight flex and this is the CPM device. I told you before that when some patient suffers stroke, then you need to provide that motion for initial few days. Till he regains his, you know how the rehabilitation works, right? There is something called neuroplasticity. So what happens is some part of your brain, because of blockage in the supply of blood to that segment, that dies maybe in 4 to 5 minutes. Within 4 to 5 minutes, if the blockage doesn't open, that part of the brain is completely dead. Okay, so then what happens is, because our neural system in the brain has a lot of synapses, they will try to form an alternate path to send those signals or to work around that. Right? So to establish the new path, you require training. Just like when you are a kid, let's say you are 6 months old, 4 months old, your synapses are forming the path, but till the path is formed, your ability is limited, right? You cannot walk because your synapses are forming the path to give the signals to the muscles in the leg. So similarly, when some part of the brain is damaged, then your neural system is again forming the alternate path because the path available is gone. So the initial time till that path is formed, your hand's disability is much more. Now what happens is that if your muscles and tendon system is not given external motion, this is why it is called the passive motion. If they are not given any external motion, they will tend to become stiff, they will lose mass. Okay, so in order to maintain that mobility, you do this passive exercise. What is passive exercise is when the force is applied externally to the hand, that is called the passive motion. When you tell me that open your hand and I do like this is the active motion because I am able to do that, right? Passive motion is when somebody takes my hand or the exoskeleton applies the motion on my hand. So CPM is a continuous passive motion. If this device will be applying the motion of the hand. Now the issue with this exoskeleton is that here the motor is actually installed on the fingers. It will be very heavy. But again, the palm side is obstructed and there is no exoskeleton for the thumb. So obviously we cannot use it for remote handling or any other. In fact, for the full rehabilitation also it is not suitable, only for that particular activity. This exoskeleton has the tendons going and there may be actuators on the remote platform and the force is applied directly at the fingertips. This exoskeleton, obviously this has the elbow hand motion also, but let us disregard that. On the hand side, there is no finger exoskeleton. It only provides platform, it only has the finger degree of freedom. That is all the four fingers together and come together, and they can give assistance like no independent motion to the fingers individual. These are some of the exoskeletons for haptics. Again, they vary in their mechanism, how many interaction points, how many degrees of freedom, how many degrees of actuation. So now I have come to the first use case, that means the exoskeleton that we have developed for the dexterous remote handling. Dexterous remote handling means we want the dexterity of the hand on the remote side. So actually till now dexterous remote handling there is no platform that is available that gives you dexterous remote handling. So what does it mean is there is a hand which is anatomically similar to the human hand on the remote side, and I can control the joints of that hand independently. Applications, as I discussed, radioactive hot cell. If you see, this is actually the real life picture of a radioactive hot cell. You will see this is the master side, that means user will be standing here holding this particular part, and what you see is the inside the hot cell. Hot cell means it's not a high temperature, it's the radioactive. That means I cannot go there to do the maintenance on the radioactive components. So this facility is installed in some accelerators like CERT, and India also has one accelerator in Kolkata. So now I have to operate, I have to, let's say, open the nuts, bolts, I have to remove certain parts and replace them. So I will be holding here and will try to move this part there and try to pick up. So you can see how difficult it will be. Even if I am looking at certain things up close, I do not get the sense of contact, then it will be difficult for me to do that task. Right? If I get the sense of contact, then my efficiency of operation increases. So this is the example of where you might need actually remote handling. This is the detailed schematics of this system, where this is the master system. There is a master arm. This is a master gripper, not the arm. This is master gripper, your master arm, this slave arm, and slave gripper. So when I move this point, it correspondingly moves. So let us say I move this as 1 feet here, this point will go 1 feet there. If I hold this part and this part together and move like this, then these jaws will be operated. But the problem here is that I am not getting the dexterity of what I could have done my bare hands, how efficiently I could have done there. Using this 2-finger grippers and using these master grippers, I may not be able to achieve that efficiently, obviously. So it will take time. So usually if you want to replace just one part, then you open 10 bolts. It will take morning to evening in these hot cells just to open 10 bolts and replace it. Another example is the biohazardous environment where again human cannot do. Handling of explosives, I don't want to be present there, like bottling of explosives, ammunition, when they fill the explosive in the ammunition, who wants to be there, right? It's better if we can offload that task to master-slave systems so that if some mishap happens, at least humans are safe. Then in space, we have to do space box outside our International Space Station. Why should we put our life to risk if we can we can have such master slave system. Then the ocean floor pressure is so high. You saw the example of Titan. It imploded. So it is risky to be at any of these places to perform any kind of work. What was the objective in this project was to demonstrate the force feedback, to develop the force feedback master and demonstrate the dexterous remote handling. So the schematic was that on the operator side, the user will be wearing the hand exoskeleton with motion sensors installed. Finger positions and angles will go to the slave side controller. Slave controller will run the position control algorithm and the robotic hand will move as per the user hand. Then as soon as the contact happens, that contact detection will happen and the interactive forces will be measured. Forces of interaction will be measured, sent back to the master controller. Master controller will actuate the actuators so that my finger motion is stopped as soon as the contact happens. Right? Till the time contact doesn't happen, if I move like this, the slave will also move like this. But as soon as contact happens, my fingers stop. But it should only stop in this direction, right? It should not stop in the other direction, the opposite direction. Because I want to release the object also. So we have to develop the hand exoskeleton, motion sensing and transfer motion to remote robotic hand, contact detection, and then the actuation and the robotic hand. What are the different components? On the operator side, we have exoskeleton with motion sensors, force feedback actuators, actuator controller, sensor controller, then the master controller means it is the IR controller, and then the video stream. So we also want to have the visual feedback. So this is, let's say, our robotic hand doing some task. We need to measure take the results using the stereo camera and stream that to the user on the user side. Now what we have also implemented is the head movement. So when this camera will move based on the head movement of the user. So if I look down, up, down to the camera. This is the exoskeleton mechanism schematic linkage system. So obviously these can be replaced by the finger or fingers. But if I want to see what is the degree of freedom of this mechanism, is 3. So as per our categorization, if you see, if the degree of freedom is 1, then it is fully constrained. If the degree of freedom is more than 1, then it is redundant. So this exoskeleton degree of freedom is 3. So that means it is a redundant system. We can actually attach here. So I am considering both side motion as single degree of freedom, whether it is for extension or flexion. Now that what does 3 means? That for a single configuration of this linkage or the input linkage, there is no unique configuration. It can vary, right? Now what you see here is how when I do the grasping, so these are three joints. Okay, all start with 0 degrees and how they end up, right? So what has been done is linkage length has been optimized so that we get the maximum motion out of our exoskeleton. So if you see the red line is this design, third design. We started with the first design. First design is black wing. If you see, this is the MCPM. So what we want is to achieve the maximum angle. So we want it as low as possible. Obviously, if you want to increase one, the other one may decrease. So we achieve through this optimization of the line in this line. What we wanted was to achieve maximum motion. Now this is the exoskeleton mechanism for the thumb. The previous one was for the finger. So mechanism remains same for all the four fingers. Now for thumb there are two actuations. One is for the flexion extension and one for the adduction abduction. So it becomes now the spatial mechanism. This is the flexion extension and the green one is for its adduction abduction. Now this combined mechanism has 4 degrees of freedom. But here degree of actuation is, the previous one degree of actuation is 1. So it is under actuated redundant mechanism. This is under actuated redundant mechanism. But with the degree of actuation is 2 and degree of freedom is 4. Now for the motion tracking, we have done 2 types of systems. One is by applying motion, joint motion tracking and directly at the finger joints. But here we had an advantage that I know that I can be this will be rotating as I will be doing the flexion extension motion. So we have applied a potentiometer in this test to measure its rotation. With the calibration of potentiometer, it gives us very linear characteristics. This theta is called the degree of flexion. So that means it includes all the 3 theta, MCP, PIP, DI. But what is the problem is that now we have to correlate this theta to this theta P joint angle. So to study that, we have developed one setup where some markers were placed on the finger and the camera was placed to detect the real-time motion of the finger, and the motion of the disc was measured using potentiometer. But the motion of this joint was measured using the camera, and we did some grasping tasks, grasping of the object multiple times. So what happens is that our motion has a set path, right? If I am going to hold this object or maybe this object, so when I approach this, I have very defined path. I tend to follow one particular path. So using that analogy, we try to obtain these angles. When theta is certain degree rotation, what should be the different joint angles? Right, that was our objective. And then after measuring this theta, at a particular theta, we will inquire what should be the different joint angle. Obviously, the limitation here is that we are actually assuming that our motion is very set. Right? If I want to do like this, then this cannot detect the difference in how you are approaching, whether you are approaching like this or you are approaching the natural grasp. These are for the natural grasp. Now the actuation of the exoskeleton. So we we have developed two types of execution system. One is using pneumatic muscles and another one is using the AC muscles. Now the pneumatic muscle, I hope does everybody know what are pneumatic muscles? Should I explain?
Yes, yes. Yes, yes.
It's not?
Yes, yes. Yesterday, okay, so you all were there. So they just apply the contractual, basically the contraction motion as we apply the compressed air, right? Because of the double helical structure, right? There is a rigid thread that is going around the muscle. Braids. Yeah, braids. So depending on the braid angle, it will have different stroke, right? So what happens is that when we push the compressed air inside, the diameter increases, and if the diameter increases, the length of the thread which is going around, that length is fixed. So if the diameter will increase, its length will compress. Right? Okay. This is one of the commercial muscle from Pesto company, which has all these aerospace grade aluminum casting, wings. But it is very bulky. To use it for hand exoskeleton, it will become very bulky, right? So what another thing is that we need two actuators. We want bidirectional force because they can only apply the pulling force. So if I want to apply the force on the exoskeleton on both the directions, so I need one pneumatic muscle to extend the finger, and when this is pulled, then it will try to close the flex the. This is called the antagonistic arrangement. Okay. This is called the antagonistic arrangement, and it is very similar to how your biological muscles work. Our biological muscle can also provide only the pulling force. For each joint, there are two muscles. For example, bicep and tricep. What happens is, when I want to move like this, then my bicep is flexing. Flexing means it is contracting and pulling like this, while the tricep is released. When I move here, then this muscle does not apply any force. All the force is applied by the tricep, and then it pulls my joint in the opening direction. Now for this application we developed pneumatic muscle actuators using 3D printed parts and some commercially available very cheap components. So one of the components is the braided sleeve. It will not cost more than maybe 50 rupees for this thing. These are the flexible pipes that you might have seen. This is used in food industry. This is also very cheap, maybe 100 rupees a meter or something like that. And then the end connectors. So what we have done with the end connectors is we have designed a screw mechanism where we don't have to. There are two challenges in developing pneumatic muscle. One is the sealing. We have to give the path to the compressed air, and we have to seal it. Also, we have to attach the load, right? So we may need some threaded joints to basically use it in our prototypes. So I don't have the section view here, but what you see here is this is like a nut. What you see inside, it has a thread. So how it is done is I'll just move on top of that the silicon tube and the braid, and I'll just rotate it and it will seal automatically. There is a converging space between them. So as it moves this direction, it seals it, and there these are M6 threads. I can use it in my application, and here I can provide the conversion. So I compared the characteristics with the pneumatic nozzle of the compressor. You will see these are the characteristics for the developed pneumatic nozzle. These are the characteristics for the compressor nozzle. Now if you see the contraction, some of the indications are not there, but this red line is for the 5 bar pressure. This is also for the 5 bar pressure. So the maximum contraction is 18% here. Here sheet 21% contraction. So to enhance the contraction, the mass is obviously hugely different. This pneumatic muscle is only 7 grams. Whereas this muscle is close to 70 grams, so almost 10 times lighter. So at 3 bar the difference is very huge. If you see the Presto muscle gives 10% contraction at 3 bar, whereas this pneumatic muscle gives 18%. Now obviously the force is higher here because its diameter is, this is the characteristic of a 10 mm diameter pneumatic muscle. Here the ID is 10 mm. Here the ID is 6 mm. Okay, so the force is directly proportional to the cross-sectional area. So the force is less, but obviously this force is enough to apply on the fixtures. Maybe if we have to apply on the knee or leg joint with any higher cross-sectional area, but here they are applying force on the finger. The smaller muscles are better. This is the step pressure. So these are the actually isobaric characteristics, means how the length changes at a constant pressure under different loads. Right? What does it mean? Let us say I have the pneumatic muscle, original length was 100. I applied 5 bar pressure. I don't apply any load, then that point will be Q. Now I don't change the pressure, I only apply increasing loads on the other end. This is the path that I will use. As I will keep on increasing, whatever was the contraction initially, so let's say initially it was 100 mm, I gave it some pressure, it contracted. Now if I apply the force, it will again keep on increasing its length. Right? So as the length will increase with the increase in force, I am going on this path. When it achieves its original length, where let's say it was 100, and I have applied such load that its contraction has come to 0. That means it has come to its original length. This is this maximum force that it can apply. So this is the isobaric characteristics. Now this is the transient characteristic when we suddenly apply the 5 bar pressure. Right, in the form of pulses. Then how its displacement is coming at 0 load itself. Obviously, here the contraction is much higher. For the Festo as compared to the Festo muscle. So the response time is quite similar.
you might have discussed the phenomenological model also. What is phenomenological model is we consider the pneumatic muscle as a combination of three components. One is the spring, one is the damping, spring damping, and a contractile element. So this is the mainly actuation component. These are the passive components. They only absorb energy. This generates energy. Then the equation is something like this. Now these components, that is the B, which is a function of pressure, that means its stiffness will be different at different pressures. Its damping will be different at different pressures. Its stiffness will be different, and Fc is the contractile force it generates at a particular pressure. Now, using different experiments, we obtain what is Fc, K, and B as a function of pressure. Now, for validation of this phenomenological model, we give a test signal, triangular signal, starts from 1 bar, 4 bar, 1 bar, 4 bar, like a triangular curve. Now we see what is the actual displacement measure. Experiment 2 shows what are the displacement I am getting when I give this triangular pressure pulse. Now red is the simulation using these equations. Can I use MATLAB to model this? Then I give the pressure of the triangular pulse. This is the displacement, that is x I get, and this x is matching quite closely with the experimental. So that was the pneumatic actuator, and this is about the motor for DC motors, actuation module using DC motor. Here we use single DC motor for both the motions. So that means, like in pneumatic muscle, we need two pneumatic muscles for bidirectional motion. But when we use motor, we can use single motor as a bidirectional for the bidirectional actuation. The schematic is you have 6 motors because we need the 6 degrees of actuation, 1 for each finger and 2 for the thumb. Now from here, using the tendon guides and tendons, these there are basically flexible wires which are attached to the disc which we are rotating using the DC motor. Now what is the advantage of DC motor? It is actually the main advantage is that it is much easier to develop the precise control, that is PID control, using the DC motors as compared to the pneumatic muscles. Another reason why we chose DC motors over pneumatic muscle is the need for load cells, because we wanted to control the force. Now what happens is that if I don't have a picture of prototype with the pneumatic muscles, so for each finger if I want to control the force here, I need to measure the force, I need to give the forces feedback. For that I am using miniature load cells. Now those miniature load cells come at around 80,000, 70,000 rupees each. So our solution will become very costly. Now if I use the DC motors in place of pneumatic muscles, actually the actuator pneumatic muscle is much cheaper than the motors. Motors will cost something around 30 to 40,000 rupees, whereas the pneumatic muscle I can make in just 200 rupees. But that force sensing load cell that I need, that is very costly. And here the force sensing I can do directly on the motor by sensing the current, right? you know that the current is proportional to the torque, right? So whatever, if I am applying some force here and my motor is stopping that force, then the current in the motor will increase. And if I can measure the current in the motor, I can get the force feedback. I can apply the force PI. I can use that motor current as a feedback to my controller. This is the setup. This is motor. This is controller. Driver. So we use DRB1873 access instruments for the driver. For the controller we use 2000 series instruments. Controller programming was done using MATLAB simply. We developed the program to use it in two modes: position control mode and the current control mode. The current control mode means whatever the motion status, it will apply the same force. That means it will be back drivable. So let us say I have the motor is in current control mode. And let us say some specific current is given. So corresponding to that, it will be applying some torque. Now, if I move my finger from here to there, so the motor will follow my finger, but the force will not increase that particular force. This is only possible if we have ungeared motor, right? Because once you have gear ratio very high, then what happens is its back drivability is gone. Now this is the gimbal stereo camera system. You will see there, this is the stereo camera, and this is the master side IMU, which measures the head movement, and the stereo camera then follows the movement of the head. You can see. The mechanism for that is called the 3-axis gimbal, and it uses the 3 servo motors to run this gimbal.
The practical application.
Same that I told in this remote handling, there is a camera on the remote side, stereo camera, okay, which is mounted on this gimbal system. This was placed on the used HMD, but basically anywhere on your head, on the user's head. So it's like in the remote handling, there is a concept of telepresence. It means you are like present there. So you are being fed using head-mounted display the visuals from the remote side using a camera, and when you move your head, the camera also moves. When you move your head right, so it's like you are present there. When you move your head up, the camera also goes up. So this is like master slave for the head movement of the user.
What is the maximum distance that can be used?
We have demonstrated it to be on the same land. So like we have used the router, wireless router. So it's like wherever that router has the range, if it is in the range of the same router, then the master slave should be basically connected either through LAN or through a network system. So TCP IP model.
Sir, the module that you were using at that photo,
This one?
just below that module is what it called?
This is IMU, inertial measurement unit.
That will be figured here.
That we had placed on the computers. So like we made one glass, 3D printed glass and placed it on that. Glass doesn't have to do anything, it's just the mechanism to place your.
Sir, it is available in market. IMU.
Yes, IMU is.
IC number, do you know it?
IC numbers actually keep on changing. Initially we were using 6050. So this is
6050.
So this is a 6-axis system. Means
That means you can measure vibration also from that. IMU, if it is inertia measuring unit, that means you are measuring I. That means Jacobian you can create.
it is already implemented in the lab.
Jacobian already you can
So
create.
actually it measures the 3 accelerations only.
The acceleration.
3 linear accelerations, 3 angular accelerations.
Oh.
That is the basic one. But when you use the library, it converts the acceleration into the rotational motion. So it can give you the angle like yaw pitch roll. So what we are using is the yaw pitch roll only.
You are measuring acceleration means you are measuring vibration also.
You can measure the vibration.
So we calculate that. No, it is not that. It is not that.
Yeah. But obviously it has linear accelerations. So if you want to measure vibrations of a certain machinery, you can implement that and get those accelerations.
Acceleration as well as the displacement also you can do that from there.
Displacements you will have to integrate.
Integrate.
It's not very good for you measuring the displacement. We
Yes.
actually tried to use it for
Roll pitch.
for the yaw pitch roll is fine.
Yes.
It's no problem. But if I want to paste here and move my hand, let's say 10 mm,
Yes.
and I want to measure that hand movement, not the acceleration, not the velocity, but the position,
Position.
I have to integrate twice. So there is drift error, a lot of integration error, because integration is happening and little bit error with time becomes very high. So you have to reset the error using some other feedback also.
Okay. And the unit that you are using NRF 24L transceiver,
Yes.
right side.
For the wireless.
For the
Wireless. So in the
For the wireless.
in the next step, because in the next step we disconnected this thing. We use here transmitter and receiver here, so that I don't, because I cannot demonstrate use by hearing this, right?
and that last module that you are using 328 at mega 328.
Yes. So if you see here, there is one Arduino Nano here also. So why is it there? Because you are.
Oh, it is integrated already.
No,
Nano is integrated at there.
Yes.
Okay. That I
So
was
this
waiting
has to
for.
be, this is battery. This has to be independent device. Right? And this is the sensor. This is the IMU sensor. It is going into this controller. Controller is getting power from this battery, and it is giving signal to this NRF. NRF is in the middle. Now the NRF wirelessly transmitting the signal to this Arduino. This is NRF, and then it is controlling the motors of servo motors.
Okay. Sir, you have used last slide Festo. What does Festo means?
Festo is the name of the company. They work a lot on pneumatics.
Only pneumatic actuators.
No, all kind of pneumatics.
All kinds of pneumatics.
All kind of pneumatics means
The manufacturer.
pneumatic cylinder, even if you see
Yes, this one.
because this component is from Festo. So all the pneumatics, they are like huge in pneumatics. Any component of the pneumatics they will make it. Even the tubes that we use to supply power, compressed air here, we get it from Festo.
Festo is a German company. I think. Okay, this is the immersive stereo feedback. I talked about the gimbal.
German company.
I think German. It's called the Festo AG. Festo AG GmbH. Yeah, it should be German. Now this is the complete system architecture. This is the complete system architecture of master-slave communication. On the slave side, so we purchased this electro-robotic hand. This is from South Korea. It's to control if we use the latte panda. Okay. Now this is communication is canvas-based communication. This is the router that I was talking about. The router is also connecting the Jackson Nano, which is controlling the motors of the stereo camera. Now this is the slave side. Now coming to the master side, you have the hand exoskeleton. The motion of the hand exoskeleton is being sent to one controller, which is sending them wirelessly data to another controller, which is converting it into basically the ROS command. So we are using ROS protocol here, starting with this controller. And there is a PC with dedicated GPU for the which is connected, which is getting the video signal from the stereo camera. Then on this pan we have the computer system, which is we are using NI FPU to control the motor and the value for the interface. This is the HTC Vive, which we are using for the immersive display of the signal coming from the stereo camera. The stereo camera signal is coming through HTC Vive, which the user is wearing. This is the contact detection. Contact detection is working and showing which finger is in contact. So here we see when I grasp using one finger, only the index finger, so that this is showing the contact has detected on one finger. As soon as contact is detected, what is being done here is, now what is the force of interaction? So let's say the robotic hand is grasping the bottle, whether it is grasping softly, whether the grasp is strong. What is the force? That force we are measuring from the current of the robotic hand. The robotic hand which was there. Now the robotic hand has current on each of the motors on each of the joints. what we are doing is we are measuring the currents on all three joints, and we are adding that, then taking average, and then predicting what is the total force, and then after the contact action, that force is applied to the actuator on the finger of the. When I did using all three fingers, so that contact is detected on three fingers. Another interface which shows the okay, so here we see index, middle, ring, thumb. So unfortunately the robotic hand that we procured, that had actually 4 fingers. So 3 fingers and 1 thumb. So the fifth finger motion was not being used. So here no contact, you can see here no contact, and then whichever finger are in contact they will show here, and whatever is the force, feedback force will be shown in these graphs. And then these will show what is the current in the current or the torque control mode of the motor. Now the advantage of that is, using this interface we can make sure by adjusting our hand that if you want a good grasp that all the fingers are in contact.
These are 4 fingers.
Yeah, these are 4 fingers. So my this finger motion is not being used. Only 4 finger motion is.
The practical application, the previous one is practical application.
Practical application is remote handling. That is what we are. That project was funded by DRDO for. Obviously, that was the first step only because we only had robotic hand, not the arm. So, if not implement the arm, then we have who actually can do practical tasks using the full robot. This was the development of master site for the robotic hand.
So what can be done? Only building or
No, anything. Your hand. Robotic hand is following your hand.
I can do that from
Yeah, you can. It will follow your basically your hand. Now this is another device developed which is the actuated exoskeleton based hand rehabilitation device. I'll quickly go through that. So hand function are, as I told, hand functions are lost. So we need to give some assistance. Another thing is that the measurement of your range of motion is actually not a very good task. That's why you will not see this happening also. But to do that passively is very difficult. To measure the range of motion, to measure the forces, to provide assistance to passively. So to overcome these limitations is to develop the hand exoskeleton. We have used a tendon-driven exoskeleton for this purpose. So how does this apply? Force is one tendon is attached to the fingertip, and then you have these supports at different flanges, and it then goes to the actuator. Now this is the formulation that connects the torques on different joints to the force F in the tendon. So for example, if I apply a certain force, how much should be the torque? What will be the torque? Torque 1, torque 2, torque 3. Now, this is another enhanced version where some auxiliary supports are also added to the mechanism. And we see that by adding the supports, we have brought the torques close to what should be these are the reference values. You see ST here. Right. That one is without only the center support. You see here this is lower than desired. This is met. By adding the auxiliary support, we were able to meet the required torque for MCB, DIP and DIP.
sir, how you are assuming that 20 Newton force is the tendon tension?
So that is what we applied. We can apply the torque. We can control the motor torque.
Is it pre-decided torque that you are providing?
No. This is just the results that I have obtained using this formulation. Using this formulation.
But you are considering 20 Newton.
Yes, continue.
You are applying F at 20 Newton, but 20 Newton where you have got? Means the data is
20 Newton is most probably not required.
no, that means it is excessive force. But why you are considering 20 Newton? Why not 10? Why not 30? I'm just telling you.
So I'll come to that. So when I come to actuator, I will cover that. Now the motion tracking. Motion tracking, we are doing using sensors. We are applying sensors and the fingers in the joint. We can measure them independently in this. And this is the GUI to show that motion of different joints to the patient. So you can see this is called the biofeedback. So it has been proven that if the user gets a feedback from the screen of his motion, if his more encouraged to perform that motion repeatedly, as you can see some effects of that happening. Similarly, this is the game which the user is playing using his hand. So there you can see one object is moving. So when it is extended, if the hand is extended, the object goes up. When I flex it, the object goes down. And using that, I have to play the game, navigate through the game. So it helps me basically use my hand actively, using active motion more and more. Right? So this is to give. Usually, what happens that if the exercise time is less, in the conventional physiotherapy, exercise time is very less. When that using the game, that exercise time is increased because of enhanced interest and engagement of the patient. Now this is the actuator. This is one experiment was done to obtain the finger force capacity at different traction states. So the question you were asking. Now see this setup. There is load cell here, and this pulley is to adjust the length of the string for different configurations. I will lock the pulley at this position, this position, this position. I measured what is the, when I apply force with my full might, what is the force I am getting, right? So when the finger is flexed more, the force reduces. Force is highest when it is fully extended. I can apply
stretched.
Yeah. So I can apply more force in this mode as compared to this. So you see the 15 Newton was the force coming as per this mechanism. But so this experiment actually my hand is healthy, right? And I actually applied a lot of force. I know that usually in practical applications you don't apply hold that much tightly. So this was just to calculate what is the upper limit. But it is 15 Newton. But we are actually not applying 15 Newton. The maximum continuous tendon force using the motors that we used for this was 6 Newton. Because that is enough to extend the weak hand. Motor current is something which is directly proportional to the torque. Motor current is a good indicator to show what is the force being applied at the time. Now this is the actuation module, where the tendon force from the motor remotely, this long tendon is there, bottom guide is there, and the price there. You see the actuator module, you will see NI PID controller is implemented on the FPGA device called SPDU. NI SPDU is there. This is the driver, Texas instruments, DRB 8873 in the SMPS for power. Now this is the cascaded control implemented for that. So the thing in here is you have this motor. So there are, you will see there are three PIs basically. One is to control the current. So this is the current controller here. This is the current control loop which lies inside the speed control loop. So there is an encoder which measures the position and speed. This is the position control, velocity control. Outermost is the position control. Okay. Now this controller, position controller, gives the reference current, reference speed. Position PI controller gives the reference speed. That reference speed goes to the speed controller based on the feedback. It generates a reference reference voltage. Sorry, reference current. Then the current controller generates the voltage. Voltage means PWM, and that PWM is fed to the driver of the motor, and that's how this current control. So the advantage of such a control is I can use it either in position control mode by giving the reference position, or I can disregard these two loops. I can directly give the reference current also from the outside. So I can use the same program for current control mode also, or the position control mode. Now one important aspect in this control is that the current is actually not constant, especially when you use the controller which is of very high, we are using 40 megahertz FPC, and there in each tip of the controller we are able to get one current signal. So if I plot that current, it looks something like this. So this is a 10 kilohertz PWM, right? The current is not constant. When the voltage increases, the current increases, voltage down, it slowly goes down. Now, when to measure the current, that is an issue. So, that means you don't want to measure the current here, it will give you wrong signal. Right? So you basically want to know when there is PWM at high, so that's when you want to measure the current. So for that, the FPGA gives you an option that when the PWM is high, it will generate a trigger, and at that trigger only you can program. We have programmed it to measure that current. When that means at the middle of the PWM, it will generate a trigger. At that time, we will ask our current measurement program to measure the current, and then the next time. So what we are doing is we are sampling here, here, here. This is some of the performance of the position control gears. These are the position gains, velocity gains. Now here, this is the step signal, reference signal given for the position, and this is the response. Now, what is the scale here? This is the millisecond. So if I say this is 178 seconds, this is 177.794. This is 200 milliseconds. This window is 200 milliseconds. So if you see, this will be hardly 10 or 20 milliseconds. So within 10 or 20 milliseconds, my position is reached by the controller. Similarly, this is the response of the velocity control, but we are obviously not using it for velocity control purpose. This is the use of the actuator in continuous passive motion mode. Now I have given a command for the motors to move. Now this opening action is being done by the motor. This motor is rotating and taking my finger. So I can control that. Should not apply more force than a particularly defined. So I can limit that force I can apply. That means if I stiff my finger, then I can stop the motor. Motor's controller will be working, but it will not be implementing force more than a particular limit. So that is required for the safety of. Maybe if I can take 5, it is already 12. If I can take 5 more minutes. Okay, so this is the third case study where we are using the exoskeleton for haptic feedback in the virtual environment, virtual reality. So we have a gripper, 3-finger gripper here inside, and what we are user side, we are using the 3-finger exoskeleton. It has the force feedback using tendons, motion sensor using these bend sensors. Here we are using this sensor, which is a wide wrist tracker, to track the global position of the wrist, and the hand finger motion is tracked by these bend sensors. Now, additional to this force feedback, we also have the haptic feedback. Haptic feedback means the sense of touch. We have used 4 pneumatic actuators here. These are the tactile feedback. So we are using on the fingertip. You see on the finger is based on this. This is a very two-green version. My fingertip will be off right like this. So there are 4 pneumatic tactors. How do they work? If when we supply the compressed air, they bulge out and give you the feeling of contact. So we have used 4 contact points on the finger. When there is no contact, then this will not be actuated. Whichever part of you get the feedback on, that part will be actuated. Now corresponding to on the slave side also, that is on the VR environment, we have 4 locations, colliders, which are detecting the contact on the remote app, on the virtual environment. This is the VR manipulator having 3 fingers. When it goes into contact with the object, based on which side I am contacting, for example, if I am contacting something like this, so my inner side on this finger and this side on this finger should show the contact. So something like that is happening here. And this is the pneumatic control. So if I can go to the demonstration directly. After detecting the contact, based on the stiffness of the object, it is low stiffness, predefined path of the current is given. So the reference current will keep on increasing as I cross the contact point. And high stiffness means the current, the feedback force should increase at a higher rate. Medium stiffness at a medium rate. Low stiffness means the current will increase at a lower rate. So the objective of the users was to detect the stiffness. So internally the computer knows, and based on that it is giving the feedback of the current to the user. Unfortunately, this video is not running very smoothly. what is happening here is the user is trying to grasp this object, and whichever colliders are coming in contact, that is shown here. That means on the index finger, only one collider is there. Only the side there, you can see the it is fully in contact with the object, right? So all the four colliders are in contact, and on this side, only one collider each is, and correspondingly, that sense of contact is coming on the fingertip. We are sorting the objects of different stiffness in different baskets. So the high stiffness object in this basket, medium stiffness object, and this was demonstrated, and the performance was measured in the form of the confusion matrix. This is the result of that confusion matrix. Large number of users were able to predict accurately the objects of low, medium and high stiffness.